Is it recording? Okay, so recording started. So I'll quickly start with an introduction. Let me share my screen real quick. Oops. Is it working? Yeah, looks like it's working. Okay, so this is the update for the cryptography track, which is the last update for this quarter for the verified zkEVM project. This one will be a bit quicker. And with respect to the cryptography track, there are fewer projects going on. The primary project that's going on is obviously just zkLib, as well as work on the VCV-io library, which I'll talk a bit about in a second, and in which Devon and Quang will talk a bit more about right after this. There's no need for a lot of slides for this track. I think the goal of the cryptography track is fairly well defined, which is to obviously have formally verified executable specifications for the types of proof systems that are used by zkEVMs, and to, down the road, once we have these, be able to obviously verify practical performance implementations, typically written in Rust, of these proof systems against the formally verified executable specs. So in short, we've got the VCV-io library here, which Devon had been working on obviously before the start of the project. And Devon will be talking a bit more about this in a second. But this is essentially the main dependence we have on zkLib, aside from MathLib, which is used for the mathematical prerequisites. And this fills into the main thing that we're working on, which is zkLib, which is a library of formally verified cryptographic proof systems, which is obviously not just about the proof systems themselves, but also mostly with the help of VCV-io, trying to build a library that makes it reasonably easy and straightforward to define a proof system and to then actually have security proofs for it in a way that down the line, with a lot of work and a bit of hope, will make it fairly easy to add new proof systems as they come along in papers, and to try and stay up to date with whatever people are using, and to be able to generate essentially kind of reference executable specifications for whatever proof system people use in the future. And with even a bit more hope, in the same way that mathematicians have essentially started using Lean productively for mainstream mathematics project, maybe we can, we'll see, kind of cryptographers potentially try to start to formalize, their own work in zkLib. And I think cryptographers are essentially considered a target audience for this library, not just obviously people doing form verification. We'll see how that goes, obviously. But that's, I think, part of the goals, and maybe slightly a slight difference with this library from, I think, past efforts to formally verify specifications. And in general, I think just formally verifying specifications of proof systems is something that hasn't been done much and is a bit of a novelty. And I'll let Quang obviously talk a bit more about this in a second. The obviously other thing that's going on is that to make these executable, there's a bit of work going on in trying to get computation-friendly types for things like polynomials and whatnot, and to not just rely on the computation-unfriendly types that are used throughout MathLib to actually prove theorems. And this is work that I think Gregor has also been doing, and it's ongoing. So this will be the work that will be discussed quickly by Devon and Quang, and I want to basically add a few more words about future plans as things progress. So the main thing is obviously adding more proof systems to zkLib. So alongside actually just making VCV-io and zkLib usable for as kind of libraries in themselves, obviously we have to populate these libraries. The approach to do this will be fairly straightforward and will just be based on establishing blueprints for proof systems that are of interest. And we've got some paperwork that started to progress towards grants for blueprints for Fry, which is obviously heavily used, as well as Stow and Were, and will be extending that effort to blueprints for other proof systems down the line, and try to be as complete as possible and to match whatever zkVMs are using. The other thing is that once we have blueprints, this obviously means that we can have implementations that are tied to security proofs that, because they're in blueprint form, will have placeholder proofs. So one way to deal with this is either to have grants for some proofs, but also to have bounties, which will basically be setting a fixed amount or fixed reward for proofs of certain theorems that have been stated and expected to be the correct expected statement that we'd like to prove. And then it'll be possible for anyone to kind of come along, do a pull request, and provide a proof for any theorem to then collect the associated reward in a way that hopefully opens things up in terms of participation, as well as makes things potentially go a bit smoother in terms of administrative requirements. Because if we have to do grant for every theorem or every kind of big bunch of theorems, that's more grants to process, and processing grants obviously takes a bit of time and effort for everyone, and in particular for bounties that are below a certain value on the admin side, it means not having to do KYC. So hopefully once we have blueprints established for Freister and other proof systems, we can start offering bounties and seeing how this goes. We'll also be thinking a bit about how to price the bounties in some reasonably smart way. And this will be, I guess, coming soon over the next few months, and potentially by the time we have another update call around June or the end of the second quarter of the year, we'll talk a bit more about this. Hopefully that should be around the time where we can start offering bounties. All of that will obviously help us get to the point where we have proof systems that have an executable spec that is directly tied to a proof in lean. The next step beyond that, so potentially around the end of this year, or definitely later in this year and much of 2026, will then be to obviously map practical performance implementations that are used by zkVMs, which will probably be written in Rust, to the proof systems that we'll have formalized in lean. This will be quite a bit of work. This will take probably quite a bit of effort, and we'll have, I think, an active discussion ahead of that around how to actually do this, what kind of tooling to use. We also have a choice of both general purpose extractions from Rust tooling with tools like ANUS. We also have a bunch of Rust verification specific tools, including tools like Verus, which are interested in developing a lean backend, and which we may therefore kind of use in that context. So I think it'll be quite open in terms of how we approach this, and it's possible that we'll experiment with different approaches and see what works best before settling on something specific. And it's also possible that in between now and the time that we start doing this, there'll be obviously further development of the tools that exist now, which will change the assessment in terms of what's best to use, and certainly kind of more practical to use and easier to maintain down the road, both in terms of the tool itself, but also in terms of if people add new optimizations to their implementation of proof systems, ideally there's a pipeline that doesn't completely break because of small implementations. And a lot of that work will obviously kind of be slightly analogous to work that's going on in other tracks, both in terms of verifying REVM against the EVM specification and trying to make this maintainable as automated as possible, and likewise for circuits, try to make sure that if there's a pipeline to verify the circuits of some certain zkVM, that the proofs aren't completely brittle and don't break down every time that there's a bit of change, or that even if there is a kind of complete rewrite, that the kind of work to actually verify things doesn't involve redeveloping a kind of verification pipeline at the very least. So that's also something that I think we'll get back to discussing a bit more towards the next update at the end of the second quarter of the year. But it is something to keep in mind, and because we're running experiments with tools like Verus in other tracks, we'll also get some reasonably useful data around how effective they might be by the time we get back to discussing this. So I think we can talk a bit about this later on in this call if there's some interest. But for now, let's go straight to hearing from Devon and then Quang, and then we can discuss future plans after that once everyone is on the same page with respect to the work that's going on now. Yeah, so Devon, if you want to share, I think we can do VCV-io and then zkLib is the most sensible order.
Does this seem right?
Yeah.
Oh, I see, but I can't do. Okay. Yeah, so my name is Devon. I guess I've been working with Quang on the only grant so far in this track. So I'm going to talk about the, I guess, underlying library we've been using to try and develop the ability to write cryptographic proofs in Lean. I think most of the work in the past has been HOL and Coq. So being able to do this in Lean was kind of we sort of needed to start all of it from scratch for the most part, although there's a lot of math foundations we can rely on from MathLib. So I guess the general goals of the framework is that we just want to provide the foundations to write security proofs in Lean. There's a couple things that are missing for that, but I think the sort of central thing you need is some DSL to represent computations that have access to oracles. The approach we take is shallow embedding, where you just sort of extend the base language, which is Lean here, with a few operations, which in this case is oracle access. This is the same thing that FCF and crypthol do, which is nice because it stays really close to the base language. And then just giving standard basic primitives and security definitions. Although obviously a lot of it's focused right now on definitions and primitives with zero knowledge stuff. And then right now there's a lot of machinery and lemmas around monads and monad transformers, which should really be in batteries, and probability distributions and calculations, which should really be in MathLib. And then I guess an overall goal is just trying to keep things really close to base Lean. It's a lot more MathLib friendly that way, which can give you a lot of, I guess, free theory and free math to use in your proofs. So the DSL we define is, we want to be able to represent a pretty arbitrary set of oracles. So we need them for non-deterministic computation, so coin flips or uniform selection, and also for random oracles. And then when we do security games, a lot of adversaries have access to more oracles. So we need a pretty flexible representation. So we define this type oracle spec, which represents some sort of type signature for the set of oracles you have. So if we have some indexing set iota, we just have a spec for the oracles be a map from each index to the domain and range of the oracle itself. And then we get a pretty simple functor to represent queries, where by functor here I mean a map from type to type. So we have this, I guess you guys can't see if I point at anything. But so we have this oracle query type, which says that if we have some specification of oracles, it takes in an output type and represents an oracle query. So there's only one constructor, just this query oracle I on input T, and you get an oracle query with output type in spec.range I. That's essentially the whole base representation of what actually a query is. And then the actual DSL we're using for the whole development is just taking this oracle query and essentially extending it into a monad using free monad and option T, which are two monad transformers. So the free monad is adding the ability to sequence computations and return values. We already can query things, and then option T lets us have a failure operation. So more explicitly, we essentially have an inductive type with essentially 4 constructors. You either query something, return something, sequence 2 computations, or you fail. In actuality, there's a lot of lean and batteries stuff going on under the hood to make these compatible properly, but in practice, you can just treat it as a type with these 4 things. It's a monad, and we haven't actually defined what queries mean, so this is just a syntax for representing computations, and we still then need to actually say how they behave. But this is essentially the whole DSL for how we're actually representing protocols in our system. I'll have some examples, but that'll make sense. So then we need some actual semantics of these computations, which we do by saying we can map into other monads, and via those mappings, we can, I guess, prove things about the original computation. So if we have some implementation of how oracles should respond to queries in terms of some new monad M, which is where we're computing the results, we can extend that to an implementation of any computation, not just queries, but anything in this DSL. If you like commutative diagrams, here's like a nice little picture, but otherwise, what we're actually saying is we have this top map, which implements Oracle query in terms of M, and then the 2 steps in generating the DSL, we can just lift along them, and then these dashed lines are maps that just exist by either the fact that the universal properties of whatever these monad transformers are, or you can just explicitly construct them. And so the resulting map at the bottom is this simulate Q, which basically says if we have a computation and we have a way to implement the oracles in terms of some new model M, then we can implement the actual computation in terms of M. So maybe makes more sense explicitly. So depending on what monad we map into, we can represent actual semantics of the program. So for instance, if we map into set, we can get the possible outputs of a computation by saying we map every query into the set universe. So essentially a query maps into any possible output, then the simulation as a whole will compute all the possible outputs of the computation itself. If set.universe was some other set, then you'd get the possible outputs of the computation for some other set. And then same with probability distributions, we can map queries into a uniform distribution, for example, and you'll get how does the computation behave if you map every, if every oracle were to respond that way. You could, in theory, also say, what if we map every query to a normal distribution or something like this, and get the appropriate semantics from it. And we can do the same sort of mapping for other functionalities. It doesn't have to just be these semantic things. So the way we handle logging and adversaries queries, for example, is to say we're going to use this writer T transformer where we write to a query log and then we keep the base computation. And we're just saying we're replacing every query with read from that query, tell the writer what you just read, and then return the query result. So you just imagine you have a computation with a bunch of queries in the middle of it. We're just swapping all those queries out for also telling the writer along the way that we got this thing, and it will build up a new computation that has all these tell things in the middle. And because it uses all this sort of monad framework to do this, it gives you really nice equalities. So this bottom line is saying if we run the computation OA with some logging, and then we take the first part, so we throw away the log, we actually get back the original computation. So there's not, I'm not saying these are semantically equal. I'm saying these are exactly the same computation, which is really nice for writing proofs because you can use Lean's rewrite and simp and things like that. Actually, in practice, maybe the simplest protocol I could show is Elgamal, except one challenge being that MATLib doesn't actually have nice finite fields to work with. So I'm using a group action version of Elgamal, but if you say G is a type of vectors and P is a type of base points, then you can think of regular Elgamal as the base points are the elements of the field and the action of the vectors is exponentiation. But the basic form is that when we're writing protocols like this, we have, we're specifying what the message, public key, secret key, ciphertext types are. We specify these three algorithms. So like in keygen, this $T is secretly a query under the hood to do some selection of an element of P. And then, you return these pairs of base points, and then for encryption, you choose a random vector and we do some division, and then there's this boilerplate at the end to do, I guess just to tell the system how to actually run the oracles in practice. But this is what actually using the DSL to actually write protocols looks like, I guess in the simplest case. And to write proofs, we have like syntactical support to do things like this, where you'd say, for example, for any message, the chance you get the message back from running keygen and then decrypting the result of encryption is 1. So that's what you'd expect a encryption algorithm's completeness to look like. And then the proof for Elgamal is tragically a little longer than you might like, because we have to do this arithmetic stuff, which can be a little trouble in some proofs. That's largely based on how much automation exists in MATLib around things. And then after that, the actual proof semantics of reducing the obvious things of probability 1 if and only if XYZ is handled by this simp tactic pretty automatically. So that kind of just happens. And then the proof is complete. It's this very simple property, but it is reasonably automated for being simple. Yeah, and then I guess overall, some short-term goals. The documentation examples are still not great, and me and Quang have also been developing fairly actively, I think. So there's a lot of sorries and roadmap things, which is maybe fine, but also if people start importing the library, I think every time they compile, it replays our errors for them, which is maybe not great. There's also a lot of the monad machinery in Lean is really nice to use for programming with monads, but a lot of the background theory to actually prove things about those computations doesn't exist. And I think the general thought is all of that should eventually go into batteries, but there is a lot of things that would be nice to get done there. And then whatever arises in zkLib, one big issue is also swapping the internal parts of the computation. This is very brittle right now, which is fine, but as we start to actually use this more, it'd be nice to have enough automation that it sort of hides that brittleness. And then we have some basic Hoare style stuff, but it's not in a great place to actually prove things with yet, I don't think. And then some larger gaps, we don't have any sort of general abstract program logic. I know there's discussion that LeanFro is going to be taking that on, but I don't know exactly what the timeline looks like for that and how exactly it'll fit into the project, or how helpful or not helpful it is. We also, multi-party and variable length protocols are something that we can handle, but it feels ad hoc. And if we had better abstractions, that is probably important long term. Asymptotic security and UC security is the other thing that we don't handle at all, really. All of the proofs we're writing are concrete security-bound proofs, essentially. I think long-term being able to talk about these well is probably good, but I also don't know how high priority or if anyone, has important use cases for it now. But yeah, that's what I have for the actual presentation. I'm more than happy to answer any questions.
You are using a free monad because of just a syntactic thing, or the query doesn't hold some, some monad law fails, or?
Yeah, I guess it's just because the base Oracle query type we start out with doesn't have bind and pure. In the past, we had like just one object in the DSL that was, yeah, like an inductive type with pure, bind, and query all built in. But our experience was that it works better with this sort of stacking thing where you have just the queries, free monad adds pure and bind, and then we get the failure later.
Okay, thanks.
I don't know if that answers your question.
Yes.
Okay, any other questions? And otherwise we can move on to Quang. Okay, I think we can move on to Quang and then get back to this later if we need to.
Okay, so yeah, let me go to slideshow. I'm not sure if it's still showing. Okay,
yeah,
I think it
sure.
does. Awesome. Yes, so this is basically my presentation for the ZK proof invited talk next week. So there'll be like some sort of like general introductions and so on that I'll try to skip because yeah, I think those in the call today already know what I'm going to be talking about. Yeah, so with that said, basically the goal of the cryptography track is to make sure that ZK snarks, as we envision it, with all these amazing applications, are actually going to be secure. And currently, this is not the case due to a bunch of different reasons, different insecurities at different levels of constructing ZK snarks. And so we have this verified zkEVM project. And what we are doing is formalizing the snarks based on interactive Oracle proofs. Okay. So, and this is going to be the focus of zkLib. So the goal of zkLib is essentially we want to mechanize the security proofs of these current snarks, and we get some verified implementations from these verified snark specifications that we have built. And so these are the broad goals, but how to achieve these goals? We would like to achieve them in a modular and compositional manner. And I'll explain what that is in a bit. And the main sort of insights that we're working towards that could allow us to state things in a modular manner is to develop a sort of program logic for interactive Oracle reductions, which are sort of the main building blocks for us to build IOPs and then to build snarks from IOPs. The hope here is that by formalizing snarks in zkLib, we could state some general transformation theorems stating how different reductions can be composed together. And we will get the whole snark that way by gluing different building blocks together. And the hope is also that this would clarify the existing constructions in the literature and streamline the security proofs. Because if you look at the snark literature right now, there are some attempts at modularizing SNARK constructions and security proofs, but I think a lot of it are still lacking. And definitely there are a lot of missing security proofs as well. Okay. So the outline is basically, I'll first remind you of what I call IOP-based NARCs, and then I'm going to work towards these sort of ongoing work in zkLib, or rather at the theory of zkLib, on having a sort of like program logic for interactive oracle reductions. And finally, I'll go to actually what's currently in zkLib and what are the immediate next steps. Okay, so NARCs, we all know sort of what that is. You have this non-interactive proof from a prover to a verifier, claiming that the prover knows a witness such that X, which is the public statement, along with W, which is the private witness, belongs to some relation. The verifier will look at the public statement and the proof and will either accept or reject the proof. Okay. So pretty simple. Most NARCs nowadays come from applying the fiat-Shamir transform to an underlying interactive proof. So here we're just adding rounds of interactions to this protocol, and we require that the verifiers are just setting nothing other than random challenges. So that's why we could apply fiat-Shamir. And finally, a lot of NARCs are also coming from this even more abstract primitive called an interactive oracle proofs. And here, everything is basically the same as interactive proofs, except that the prover's messages are only available as oracles to the verifier. So let's say the message is like a vector. The verifier cannot see this vector in full, but it can query individual positions of this vector, and the prover will respond with, what are these positions? So this is the sort of like information theoretic core of this whole pipeline of constructing SNARKs. And if you look more closely at these IOPs, they're actually, in papers that describe IOP, they are usually described as a series of interactive oracle reductions. So here, a reduction is different from a proof in that you don't reduce fully to the verifying saying yes or no. You reduce to some intermediate relation, say, some intermediate relation, and then from that, you may reduce it to a further, simpler relation, and so on and so forth, until you get to the final sort of trivial relation that is yes or no. And here's an example of such a reduction. So this is the famous sum check protocol, and I'm just explaining here for two variable case. So let's say you have a bivariate polynomial p in two variables x and y, and the relation is that we want to show the sum of p over the square is equal to some target t. So that's the input relation, and the sum check protocol will reduce this relation to some output relation where you have p evaluated at some r1 and r2 is equal to some other value. And these are all the things that will be sent during the course of the reductions. So for the two variable case, the protocol proceeds in these two rounds, right? In the first round, the prover sends this S1 polynomial, which is supposedly equal to this expression right here. And then the verifier will check whether S10 plus S11 is equal to this initial target. And then second round is sort of similar. Prover sends another polynomial S2, which is supposedly equals to P at R1 and X. And then the verifier does some checks. And then finally, it outputs this T prime, which would be S2 evaluated at this random challenge R2. So this is the sum check protocol. And I'm sure many of you are familiar with this protocol. What I hope to do, and I have been doing in zkLib, is to break this protocol down further and further into just components reductions that are trivial to establish security, and then gluing these reductions back together using generic transformation theorems. So let me demonstrate what I mean by this. So in terms of decomposing the subject protocol, the first obvious thing we could try to do is that we decompose this into two reductions that are composed together. So we just cut off every round, and in each round you get something like this. So now you have introduced a sort of middle relation that basically states that PR10 plus PR11 is equal to this S1R1. So that's the intermediate relation. Okay. So this breakdown is quite natural, but in fact, we can do even more. We can break this down into a single message reductions. So let's take this first round and break it down further into first the prover only sending S1 to the verifier. And then the middle relation will now be something like Px0 plus Px1 is equal to S1x. And the equality are as polynomials. Okay. And then you send back this random challenge R1. And then the middle relation, now you just replace the variable x with the challenge, random challenge R1. And at this point, I think it is clearer that these reductions by themselves are complete and sound. And so more concretely, if you look at the probability of the reduction failing, which is basically the verifier accepts whatever claims it tries to check, but the output relation is not satisfied, then from Rn to this Rmid prime, there is no probability of failure. You can just work this out deterministically. And for Rmid prime to Rmid, you have this probability of failure to be at most d over the size of the finite field. And this is a basic fact about polynomials. So we have decomposed the messages to be like this. And another benefit of decomposing things like this is that we have these round by round guarantees that come for free. And this is sort of a technical note, but we actually need these round by round or state restoration notions of soundness so that when we compose with Viet-Shamir, we actually get a snark. Okay, so this way we also get these guarantees basically coming for free, because for a single message reduction, there is basically an obvious way of stating the round by round state function. Okay, so now we have decomposed it into individual messages, but I claim that we can even abstract this out further. So what the new layer of abstraction is the concept of a virtual polynomial or a virtual oracle in general. So here, basically, if you define this P1 of x to be equal to the sum Px0 plus Px1, then you can simplify a lot of these this protocol. And you can see that here, for instance, the first protocol where you send S1 is just checking whether S1 is equal to P1. And so this makes the sort of the protocol even more obvious. Okay. And so this is also one of the things that zkLib is doing, is that we try to formalize these virtual protocols in full generality so that the same patterns of virtual protocols show up in many different IOP constructions, and we need to abstract them out and actually apply them in a uniform manner. Okay. So that's the general approach of zkLib. And this approach actually has connections to sort of classic techniques in program verification. And in particular, we can look at, say, the Huar triples, which is developed by Tony Huar and also Robert Floyd almost at the same time. And a Huar triple says that if we annotate a program C with some precondition and postconditions, then we can have a bunch of rules for reasoning about programs based on various preconditions and postconditions. Now, I propose that we have something similar here, namely that we have an IOR, And the RR takes some input relation R1 to some output relations R2. And we have basically two security games, completeness and round-by-round knowledge soundness. Can we get a similar rules for IORs as with rules, hard logic rules for many different kinds of programming languages? Here, the programming languages is whatever language that allows us to express these IORs. Okay. So this is sort of an ongoing work on the theoretical backings of zkLibs. Now, finally, I want to talk about what's actually in zkLib right now, and what Alex suggests and what we plan to achieve in the next few months. Okay, so right now what we have are just the basic definitions of interactive oracle reductions and the basic definitions of their various security properties. And we only focus on the straight line extracting case right now. We also have been able to specify these simple IORs, such as the single round of sum check that you've seen before. And we've managed to prove completeness and round-by-round knowledge soundness according to the blueprints that I just showed you. And we've also started to define these computable polynomial data types for, say, univariate and multilinear polynomials using sort of underlying arrays, so that the hope is that they can be efficient when compiled down into C. Okay. So in terms of what will happen in the next few months, the first is that we plan to mechanize these transformations. So you can sequentially compose IORs together, and we can specify what it means for an IOR to use a virtual protocol. And we also need to prove that these transformations will preserve the security notions. We will also give a case study of these ways of composing IORs, which is that we want to formalize the Spartan polynomial IOPs and also possibly the Ligero polynomial commitment scheme as itself a vector IOP. And we also want to continue having these correspondences between the polynomial computable data types with the MathLibs abstract data types. So this has been ongoing and mostly finished for univariate. We still need to do more for multilinear. And then thanks to this, we'll be able to have an executable implementation of the Spartan PIOP using those types. And hopefully we could cross-check our executable implementations with existing Rust implementations. And as Alex said, there will also be lots of blueprints coming for properties of read-only codes and also formalizing Frey, War, Plonk, etc. So we'll hope to get zkLib in a good enough stage so that more contributors can come in and formalize these protocols. I also talk very briefly about sort of more long-term goals. The first is that we want to also formalize this compilation procedure, right? And I think there is a possibility here that they can be captured by the same sort of program logic framework that I described earlier, but I don't have anything concrete yet. So maybe I'll show you at a later date. The second thing is that there are many protocols which do not have straight line extraction and relies on rewinding. So we will need to formalize what does it mean to rewind and formalize the main theorems of rewinding knowledge soundness. And we also need to formalize zero knowledge. None of what I said mentioned anything about zero knowledge. And finally, in terms of getting actual implementations, I see basically two paths here. On the one hand, it seems possible that if we really optimize the underlying data types and optimize the functions, then we can actually get a pretty good verifier's performance where the verifier is written in Lean. But alternatively, if people really want a Rust verifier, then we could rely on hopefully upcoming tools to establish functional equivalence with the zkLib's specification of the verifier. And of course, lots of tutorials and documentations are on the way. So that's basically the end here. And yeah, just zkLib is our attempt to build a lean framework that can formalize your favorite snarks, especially if they are based on IOPs. And the key ideas is just we want to make this as modular as possible and leverage existing ideas from the field of program verifications. And that's that.
Thanks a lot. Any questions from anyone?
Could you elaborate a bit more on this virtual protocol as part of the proving that you mentioned? So this is not what is the subject protocol is using in its theoretical proof. It's something we need here for zkLib.
So I think of these virtual protocols as a convenient way of stating various reductions. If you look at various protocols, even Planck, like Planck invoked this sort of permutation check, right? And if you look at the permutation check, there is a sort of simplest form of the permutation checks. And there is the form that Planck uses, which sort of Planck has these polynomials. You convert them into the format that is suitable for the permutation check, and then you run that check. And that is invoking a virtual protocol. And you'll see this occurring all the time in various like snark constructions as well.
Yeah, so it's kind of some intermediate proving step you need to check for the equivalence.
Yeah, so in sort of program verification terms, this is a sort of like goal state. You don't necessarily have to write down these in your implementations, but these are here in the specifications so that you can reduce the duplication of proofs and also make the structure clearer.
Okay, thanks.
Yeah, I'm happy to talk more after this.
All right, any other questions? Yeah, and I think actually one interesting point you mentioned in the end was obviously potentially being able to generate reasonably performant code from Lean, which would potentially be quite nice, even for fuzzing purposes. And we'll see where the Lean throw gets to with that as well. But I think so. One interesting thing that I didn't mention at the start is obviously that we're doing all of this work in Lean essentially, but it would be quite interesting to think of an angle that involves obviously some people outside of this was interested in interoperability between different proof of systems, and maybe that would be interesting to have as well down the road, given that you have other libraries like SSProve in Rock and similar efforts, and we'll probably talk about this at Hacks. I think there'll be a session related to this, but that would be a fairly interesting angle to explore as well, down potentially very much down the line, but in terms of kind of allowing other contributions, or kind of given that there's some expertise in Rock and EasyCrypt, things like that, around these kind of Hoare-style logics, that could obviously potentially help. But we'll see what comes up at Hacks next week related to that.
Yeah.
But yeah, hopefully, so this should give everyone a good overview of what's going on with VCV-io and zkLib. So I don't know if anyone has any kind of broader points that they want to bring up, and if not, then we can hopefully finish up this call in the next few minutes and actually manage to keep it within an hour, unlike the other ones. Okay, then I think we can wrap this up. So yeah, as I said at the start, we'll have blueprints coming that'll be in the works soon for Forest-Delaware. There's some Plonk related work that will also be going on at some point. Sorry, Julian, go ahead.
I mean, I didn't mean to interrupt. I guess that's the point of putting a hand up. But I just wanted to say very quickly that Ilya started the work on Fry implementation using zkLib literally yesterday. So, but we'll talk about that later. Sorry for interrupting.
No, I think it's the right time. So yeah, like I said, basically we've got Forest-Delaware and Plonk related work coming, and we'll talk a lot more about this by the time we get to the end of Q2. And yeah, at that point as well, we'll be talking a bit more about both the code generation angle and tying things back into Lean, and hopefully we'll potentially have more examples to do in zkLib. I think very recently, Devon and Quang managed to get a simple one-around sum check protocol to kind of go through, which is, I think, the first, I guess, kind of real and interesting proof that we've had in zkLib, and so we should have a few more examples coming up over the next few months, as Quang said. And so there'll be things for also people to kind of look at and to learn from, and so we can all look forward to that, and hopefully also then by the next update at the end of Q2, we'll also have more people contributing and more to talk about in that sense as well, and a better sense of how usable things are for people who aren't, I guess, the initiators of both VCV-io and zkLib, and we'll try and work to make everything as usable and nice to learn as possible. And yeah, I guess on that note, I'll end the recording, and we will. I'll say actually one thing, I guess, for anyone who's watching this later on. Obviously, we have zkLib meetings every 2 weeks, and so if anyone has made it to the end of the recording and wants to contribute and is interested in hearing more about zkLib, that's obviously one way to get involved, is to attend these meetings, and you can get in touch via Telegram or whatever else to do that.